All right, welcome to Entanglement 1. We're continuing on. I'm Robert Nemeroff, your host for Physics X, continuing on with extraordinary concepts in physics, which is what this class is all about. So trying to get through the coolest concepts I can find, concentrating on concepts instead of math. So this is a course being taught at Michigan Tech for actual credit. There are actual students in this classroom right now. So you can find this wherever you found it if you're on the web, or you can go to find it on Google with the right search words, or you can go to some place called Starship Asterisk. What's that? We'll go to this, try to expand this and go there, and you'll find the lectures practically in sequential order at this point. So let's talk about entanglement. The last several lectures I talked about double slit experiment in detail, and I'm still not done with the double slit experiment. It is so strange you can look at it from many other ways. But let's take on a slightly different angle before we come back to the double slit experiment called entanglement. So what is entanglement? Entanglement is when two particles, they share a quantum state. So two particles are linked. They're separate. One is here, one is there, but they are still somehow linked, and they're entangled. Now, you can create entangled particles by having them, two particles created at the same place at the same time. Also, a collision can create an entanglement between particles. Entanglement typically involves momentum, sometimes angular momentum, and many times the easiest thing to measure definitively is spin. In terms of photons, it can be some kind of polarization. So we'll be looking at entangled particles here and in the next lecture. So one way to create entangled particles is to have something decay. It can be some generic kind of element, but if you wanted to put some kind of name on it, it could be positronium could be one. So positronium is where you have an electron and a positron orbiting each other. So the electron and positron are antiparticles of each other, so they attract, and there could be a problem if they touch because then they would explode. But that's only a problem if lots of them explode. I guess if only two of them explode, you get typically two daughter photons. So one photon will go off this way, usually shown by a squiggly line. One photon will go off, say, that way. And these daughter particles of positronium would be entangled, would have entangled spins, they would be opposite, and they would have entangled momenta, they would be opposite. This whole idea of entanglement really came about as Einstein struggled to understand quantum mechanics. Einstein didn't like the Copenhagen interpretation of quantum mechanics. He understood, particularly by 1935, that the experiments of quantum mechanics weren't going away. And he thought quantum mechanics was an incomplete theory and that they just had to work harder to get to the details that weren't uncovered. So the way I think of it is that electrons had, hair, bells, and whistles on them, and we just couldn't discern that just now. So because we didn't have the equipment to see all the bells and whistles on things like electrons and photons and protons, that we just had to consider what's going on there statistically because we didn't have the mechanism to figure it out. So that is sort of a hidden variable theory. There's little variables that go into describing these things that weren't known. Otherwise, quantum mechanics would have to show what Einstein famously called spooky action at a distance. So things over here seem to affect things over there instantaneously. And Einstein considered that unacceptable because he was the architect of special relativity where communication could only be done at the speed of light. So he wasn't happy with that possibility. So this went on through Einstein's life. Einstein and two co-authors, Podolsky and Rosen, later, after a lot of the quantum wars had died down, came up with the idea of entanglement affecting things. So the entanglement that Einstein originally envisioned, I guess, was more involved in momentum, but typically it's recast in terms of spins. So Einstein realized that this whole idea of entanglement could be useful for understanding quantum mechanics better, and so he started to explore that. So it took Einstein years. So if you think this stuff you're mad at yourself for not understanding, the last lecture or some page on Wikipedia about quantum mechanics so well, Einstein spent years, and he knew all of this, all of the experiments. He knew, obviously, special relativity really well. So this is strange stuff. So don't be angry at yourself if you don't get it right away. Of course, I don't get it right away. I'm more or less repeating things I've memorized to some degree, but I've thought about it a little bit, so I perhaps can add some insight. An unexpected person came out with the next the next increment of quantum mechanical, quantum leap, one might say, of quantum mechanical understanding, and that was Bell, as I've alluded to in previous lectures. He wasn't known generally for doing this. He was a rank-and-file worker at CERN, but he came up with some really good thoughts that we're going to cover next time, and this time. I'll tell you the answer here, but you'll be fun trying to get to this answer. Quantum mechanics statistics win in the end. So as strange as it was, as much as Einstein didn't like it, and Einstein actually didn't really like the Copenhagen interpretation more than quantum mechanics itself. He helped invent quantum mechanics, but the statistics inherent in quantum mechanics win. So let's... well, he knew it. It kept winning right up to the end of his life. So somebody asked, did Einstein know that? So we have discussions afterwards, so I can ask, so I don't want to, I've timed this, so we can answer that later, but I'll give it a little bit. Einstein knew a lot up to the end of his life, but this debate continues today, so he couldn't know what's been happening since then. So entanglement is usually phrased in terms of easily measured spin, and usually between two particles. One is measured by person A, usually called Alice, and person B, usually called Bob, and it hinges on total angular momentum being zero. In particular, the spin angular momentum has to be reflected, so one particle goes off in this direction, and its spin is like this, and the other particle goes on this direction, and its spin might be like that, and that is, these two particles are entangled, and we go from there. So here's a question for you to think about. If Alice, person A, measures the spin of her particle to be spin up on the z-axis, will Alice know that Bob will measure his entangled particle to be spin down on the z-axis before Bob knows it? The answers are possibly yes, Alice is that smart. No is number 2. That would require faster than light communication. 3 is yes, but only in a statistical sense. And 4 is it depends on how much Alice is paying her psychic. Because if you go with those cheapy psychics, you don't know what you're getting. You really need to go with the expensive ones. Okay, so you can contemplate that for a while. Now you're done contemplating because you've moved on to the next slide, or you haven't paused the video. So Alice, it turns out, is really smart. In fact, Alice knows that if Alice and Bob both measure the z-axis spin, that they will always get the opposite spin from each other. If they measured it on the x-axis, there wasn't, so you can consider the particle moves on the y-axis. So there's two axes here that they could measure things on. One can be the x-axis and one can be the z-axis. And I always get that mirror. Somebody says, oh no, z should be on this axis. It's conceptually similar. So if Alice and Bob both measure the x-axis, they'll continue to always get the opposite spins. So the next question is, does this by itself mean that Alice and Bob can communicate FTL, which means faster than light? Faster than light. FTL. Yes, no, maybe so. So you can think about that. That's where I've been going for a little bit of this. And the answer is no. It could be that the particles are created each having opposite spins. This could have been done with tennis balls, for instance. The correlation requires only conservation of momentum, not faster than light communication. So you could have two tennis balls being created, one spinning up, one spinning down, and if you measure the one that's spinning down, you know the other person is going to measure the one spinning up at any time. So that doesn't really require faster than light communication. The particles are created with attributes that are frozen is part of the hidden variables interpretation of quantum mechanics, though. So the idea of tennis balls is more of a hidden variables kind of thing. The tennis balls, everything is determined right when the tennis balls are created. Is that true of quantum mechanics? So next, Alice measures her particle's spin up on the z-axis, and Bob measures his particle's spin on the x-axis. So they measure now on different axes. Now, one of the strange things about this is that in classical mechanics, you can have any fraction of spin. So if your tennis ball is spinning on the z-axis and you measure its spin 10 degrees off the z-axis, you're going to get less of a spin around that axis. However, if you do it 90 degrees off on the x-axis, you're essentially measuring perpendicular. So there shouldn't be much information there. So what spin will Bob measure? Well, spin down, the opposite of Alice, spin up, the same as Alice, half the time spin up, half the time spin down, Or is Bob getting dizzy at this point with all of this spinning? So we will go to half the time spin up and half the time spin down. So it turns out that Bob's measurement is independent of Alice's measurement. Bob cannot tell from his measurement that Alice even exists. Right? So Alice could be across the hall measuring all kinds of stuff. And if Bob is in here measuring stuff, he could measure spin up, spin down, spin up, spin down, spin down, spin down, spin up. He has no idea what Alice is measuring. Alice could be getting all the same things, and that would be strange because that would violate conservation of spin momentum. Or it could be getting all the opposite things, or it could be getting the same half the time. So it turns out that if Alice is always measuring on one axis and Bob is always measuring on the other axis, they will only agree half the time. It's 50-50. If they always measure on the same axis, they will always get the opposite of each other. But correlations between Alice and Bob can only be found retrospectively. Only later, when Bob writes down, oh, I got up, down, Bob says, okay, look, here's Bob. I got up, up, down, down, up, always on the z-axis. And so Alice would then say, oh, let's see, I got down, down, up, up, down on the z-axis. Only later could it be found out that they're opposites. Still, when one measures one, the other measures the other. But in quantum mechanics, it doesn't matter what axis you measure on, you're always going to measure, assuming it's a spin half particle, that you're going to measure a spin. So unlike classical mechanics, in quantum mechanics, you have to measure a minimum amount of spin in this case. So that's different about quantum mechanics, and it turns out, oddly enough, that knowing that they spin this way and then this way, but then if Alice measures it on the x-axis and Bob on the z, that they're only 50%, it seems like that if you could communicate which axis they would be measuring on and predictions that would happen, that there seems that how do the particles know? How does Alice's particle know to be opposite of Bob's particle when Bob could have measured on the different axis? So if Bob measures x and Alice measures on x, how does Alice know to be opposite? How does Alice's particle know to be opposite of Bob's? That's a mystery, because it could have been measured on the other axis. Only later, when you compare the two, where they found that when they measured on the same axis, are they opposite. You cannot use this, therefore, for communication, because you're always measuring 50-50. This entanglement has an effect on the principle of locality, which states that objects can affect only their immediate surroundings. We'll talk about this in the next lecture, Entanglement 2. Entanglement appears to violate locality, but not in such a way that allows distant observers to send information to each other faster than the speed of light. So it's very strange stuff. But we will talk about that, and we will talk about Bell's theorem next time. So see you then. Entanglement is when two particles, they share a quantum state. So two particles are linked. They're separate. One is here, one is there, but they are still somehow linked, and they're entangled. Now, you can create entangled particles by having two particles created at the same place at the same time. Also, a collision can create All right, welcome to Entanglement 1. We're continuing on. I'm Robert Nemeroff, your host for Physics X, continuing on with extraordinary concepts in physics, which is what this class is all about. So trying to get through the coolest concepts I can find, concentrating on concepts instead of math. So this is a course being taught at Michigan Tech for actual credit. So let's talk about entanglement. The last several lectures I talked about double slit experiment in detail, and I'm still not done with the double slit experiment. It is so strange you can look at it from many other ways. But let's take on a slightly different angle before we come back to the double slit experiment called entanglement. So what is entanglement? Actual students in this classroom right now. So you can find this wherever you found it if you're on the web, or you can go to find it on Google with the right search words, or you can go to some place called Starship Asterisk. What's that? We'll go to this, try to expand this and go there, and you'll find the lectures practically in sequential order at this point.